Hi guys, welcome back to Data Every Day. Today we're looking at a data set of Olympic athletes, and we're going to try to predict whether a given athlete won a medal or not, based on a series of features. Alright, so let's get into the notebook. We'll be using TensorFlow, and I have some imports here that we'll be using today. NumPy and Pandas just to work with the data, matplotlib.pyplot, and Seaborn for visualization. We'll use the standard scalar and train test split function from sklearn for pre-processing, and like I said, TensorFlow for the model. Then to evaluate the model's performance, I'm just going to use classification report and confusion matrix from sklearn. Alright, so I'll go ahead and import those, and the first thing I want to do before anything is I want to seed TensorFlow. So the reason I do this, tf.random.setSeed, is just so that if anyone else wants to work with the notebook and you want to reproduce my results, use the same seed as me. I'm just using 100, could be anything. Then let's load in the data using pandas.readcsv. And we can get the file path over here. The CSV file we're using is athlete events.csv. We paste that in, take a look, and we have 15 columns. It seems like there's going to be a few columns here we're not going to need, like ID and name, and then it also looks like we have a redundant column here. Year and season are both taken from the games column, so games we can drop as well. Alright, let's get some info. We also want to check for missing values and data types, and you can see we have at least some missing values here. So let's check this out. Well, you know, the first thing let's do, let's work with the medal column. So the medal is what we're trying to predict. So that's our label column. So let's create the labels. So I want to predict if a athlete will win a medal, not if it's gold, silver, or bronze. So what I'm going to do is transform this column like so. If we take this medal column, it has a bunch of missing values, and if not, it has a gold, bronze, silver status. So we're going to apply a lambda function to this column. Now for every x, which is one of these, if the string of x, which means the string form of it, does not equal nan, so it basically, if it's not a missing value, x will be 1. And otherwise, x will be 0. So it will just become a column of 1s and 0s, where 1 means they were a medal winner and 0 means they weren't. So we'll make this the new medal column. And now if we were to take a look at the data again, you can see it's now 0s and 1s. So I do that first because now we're going to worry about missing values, and I didn't want those ones to get in the way. So cleaning. Alright, let's start by dropping these unnecessary columns. So data equals data.drop, and the columns we don't need are ID, name, and games. And we're dropping from axis 1. And now let's check the missing values. So data.isNA will be true and false. There will be a true value if there's a missing value in that spot. You can see NaN, so we have true. If I sum across the rows, we can get the number of missing values in each column. So it looks like we only have 3 columns with missing values. And I also want to know how much is this in proportion to the data set. So instead of doing sum, I can do mean to see the percentage of missing values in each column. So 23% and 22% in these two, and there's only 3% in age. So these are still relatively low numbers. So we can fill in the missing values with the means of the column. However, because this data set is on real humans, and because not all humans have the same height and weight, what I mean is gender plays a role into someone's height and weight. we're not going to just fill them with the straight up mean of the column, we're going to fill them with the group means. And what I mean by that is you can call group by on a data frame to group the data frame by some number of columns. So let's group by metal and sex. And this looks like to visualize it, for example, let's take the mean. Here, I'll show you. We could iterate through and print all the values, but I think it's easier if I just show you the means. So it separates them into groups. So it groups them by metal first. If they had if they didn't win a medal, then we have the means for a female that didn't win, and we have the means for a male that didn't win. And if they did win a medal, we have the means for a female who won, and the means for a male who won. So these are better means to fill for each missing value, because this is, you can see there's a clear difference. I mean, it's not too substantial, but these are the ones we care about because those are the ones that have missing values. Year we don't care about because there are no missing values in year. But you can see that there is a higher weight and higher height in the males than in the females. And additionally, it looks like there may also be higher weight in the people who won, just in general. Height as well, just by a bit. So these are better means to use. And since these are actually should be integer values, I'm going to type as type numpy.int so we can get them as integers. And all we have to do, so if you think about this, this is taking the mean of each group, right? So group by actually separates it into groups, and then the mean takes the mean of each group. So there's 4 groups in total. There's the first group, second group, third group, fourth group. So if I were to index this at just a single column, let's say age, we just get the mean for the age, but a mean for each group, but just for age, right? So we can actually use these means to fill in the missing values in the group. This is a bit confusing, but I'll try to explain. Group by creates references to the actual locations in the data frame. So if we fill the group by with the means of each group, we'll actually be filling the real values in the data frame itself. So let me show you what I mean. If we were to, let's do it this way. Instead of taking the mean, no, sorry. This would just be a, how do I explain this? Okay, so let's apply a lambda function to this. So this is just it's sort of, alright, it's 4 groups, but each one contains the age values for a given group. So when we apply a lambda function to it, x will be a group, and so we'll be applying a function to each group respectively, and the function we want to apply is fill_na. So it's going to fill all the values in the group with a given value, which will be the mean of the group. So we're actually filling each group missing values with the mean of that group, and that's just for age, but we want to do it for age, height, and weight. So for column in age, height, and weight, we can just change this to column. Let me just show you what this does first. If I were to run this, you can see it has filled in all the missing values. So instead of doing this for age, we're going to do it for column. So it'll, and we also want data subcolumn to be this new filled version of it. Alright, there we go. Now let's print the total missing values. Data.isNA. This time I'll sum over the rows and the columns to get the total number. So we have no more missing values. We're ready to move on to encoding. Yeah, so let's take a look at the data now. No more missing values. There are some categorical variables here that we're going to want to encode. So whenever I want to encode, the first thing I'll do is, you know what, I just realized. Let's make this as type numpy.int. Because right now these have been turned into floats, but we want the means to be actual integers. I mean, it doesn't matter too much, but run that now. Oh, we can just, instead of doing as type, we could do it this way. Yeah. Sorry. This is my I'm not so used to this group by thing, but it's very useful, very cool. Like, if we had just filled with the means of the whole column, we probably wouldn't have as good results as we were going to get. Okay, so now let's get a list of, let's get the length of each, the number of unique values in each categorical column. So I'm going to make a dictionary that's going to map a column name to the length of unique values in that column. That's for every column in data.selectDtypes object.columns. So select dtypes, if I just run this little segment here, it will pick only the columns that have a data type of object, which will be all the categorical columns. If I get the dot columns of it, it will just be the names of the columns. So I'm iterating through all these names, and I'm going to return a dictionary that maps the column name to the length of unique values in that column. So we can see the number of unique values in each categorical feature. And based on this, we can figure out how to encode. We see we have at least two columns here with 2 values, and that means these are binary columns and can be encoded with a binary encode function. The rest of them are nominal. They have a number of values, and they don't take on any specific order. You can tell that just by looking at them. There's no categorical feature here that takes on an order, so it's not ordinal features. So we'll make a one-hot encoding for that. Alright, so for the binary encode, we'll start by, we got to pass in a data frame, some columns, and some positive values. And then I'm going to start by creating a copy of the data frame. And for each column and positive value, in zip of columns positive values, so zip will pair up the lists element-wise into tuples so that we can iterate through them 2 at a time. We're going to take a given column and apply a lambda function to it. It takes in an x and returns 1 if x equals the positive value, and otherwise we'll fill with a 0. So 1 if x is the positive value, otherwise 0. So this is similar to what we did before with the metal. This time we'll specify a positive value for each column. And then at the end we can just return df. Whoops. This is... Oh, I forgot else. Alright. Okay, now one-hot encode is going to take in a data frame, a list of columns, and a list of prefixes. We'll start again by creating a copy of our data frame. And this time, instead of iterating through columns and prefixes, columns and positive values, this time we'll use prefixes. So column prefix in zip columns prefixes. Dummies will be pandas.getDummies. This will just get the one-hot columns for a given column and with the prefix of our choosing. Then we're going to concatenate the original data frame and the new dummies columns right next to each other on axis 1. And then we're going to drop the original column from which we created the dummies. Okay, so there are our functions, and now we can encode. So data equals, well, first we'll do the binary columns, binary encode. We'll pass in data, we'll pass in some columns. So the binary columns were sex and season. And the prefixes, the positive values. So these are the values in each column that were, positive is arbitrarily defined, but the convention is to use male as positive. And why don't we do summer as positive for season? So M and summer. And then we will one-hot encode the other columns. So pass in data. Our columns here is going to be, they're going to be team, NOC, city, sport, and event. Alright, then we need some prefixes to go along. How about T, N, C, S, and E. This is the first letter of each column. Alright, we'll run that. And why don't we print out the remaining non-numeric columns. And so to get that, we can do data.select dtypes object dot columns, and then take the length. No more. So we are fully working with numeric data, which means I'd say is a pretty good time to visualize some correlations. So I'm still not going to do correlations for the one-hot columns because there's just so many. If we look at data now, there's 2,294 columns now, and most of them are one-hots. So what we're going to do is just get these first 7 columns up to metal. So data.loc, all rows, but just the columns up to metal. That'll be just this subset of the data, and then we can get the correlation matrix for that, and store that in core, and then we can create a new matplotlib figure, a fig size of 12 by 10, and we'll create a seaborne heat map of core, turn on annotation so we can see the actual correlation values, set the minimum to -1, and we can give it a nice color map. Mako is good. And we'll show it. And we can see. Alright, so first thing that I see is that there aren't, the only really high correlation here, really strong correlation, is between height and weight. And that's understandable. But it's not, because they're still, I'm going to keep them both. They're not like dangerously high. 0.8 is pretty high, but I'm sure they'll both contribute information to our prediction. Additionally, so we don't really see any really really high correlations to the point of redundant features, but we will notice that the metal column, which is what we're trying to predict, is not really correlated with any of the other columns. So if we get good prediction accuracy, it's not going to be because one of these columns is saying everything. I mean, of course, we don't know anything about the one-hot columns, but there's just way too many to plot on a heat map. Okay, so let's split and scale the data. I'll take a look at it. And we're going to want to scale it so that each column has mean 0 and variance 1. So first let's split it into x and y. Y will be what we're trying to predict, which is just the metal column. So we'll make a deep copy. And then x will be everything except metal. So we're dropping metal from axis 1, make a copy of that. Alright, then I'm going to create a new scalar, which will be a standard scalar from sklearn, which will do just what I said, give each column mean 0 and variance 1, so that most of the values in each column are lie between 1 and -1, and each column's mean is at 0. Alright, so scalar.fit transform x. So we're just transforming x, storing it back in x. Then we'll use the train test split function to split into a train and test set. X train x test, y train y test equals train test split x y, train size 70%, and we'll include a random state of 100. Alright, now we can train. So I'm going to set up a Keras model. We'll have an input layer. The shape of a given input will be the length of our feature vector, which if we look at x.shape, it's still splitting, just give it one sec. So we have 2,293 features, so I can access that with x.shape sub 1. And then we'll create two hidden layers, dense layers with 64 activations, and a ReLU activation function. Pass in the inputs, make a second one, this one we're going to pass in x. And outputs will also be a dense layer, but only one activation with a sigmoid activation function, passing in x here as well. This will be a probability value between 0 and 1. That will be what we'll use to classify if there is a winner or not. So if it's over 0.5, we'll say that that's a winner. Under 0.5, they did not win a medal. Model equals tf.keras.model. Pass in inputs and outputs. And then we'll compile it and fit the model. So we'll compile with the atom optimizer. Loss will be binary cross entropy. And metrics, we'll use accuracy and AUC, since I believe we have an imbalanced classes. Okay, let's actually take a look at the class distribution. So I'm going to put the so this will be positive to negative. So I'm going to put the mean of y. Note that y is just this array of zeros and ones. So if we take the mean of it, it'll be the sum of the ones divided by the length of y, which will be the percentage of positive values in our data. And I guess we should do this on y train actually. But let's multiply by 100 and give it a percent sign. And then we'll also include 1 minus the mean. Times 100. Okay. And why don't we'll do one decimal place. Okay, so we can see the class distribution is 14.7% positive, 85.3% negative. So because it's so imbalanced, we're definitely going to want to use the AUC metric so that we're not just relying on accuracy to know how well our model is performing. Alright, then history. We'll store the model's fit history in history. I'm going to train on the train set, x train, y train. Then a validation split of 20%. Batch size 32. Epochs 100. And I'm going to include a callback function. tf.keras.callbacks.early stopping. So this will monitor a value. We'll monitor validation loss. And when we notice that it has stopped improving for 3 or more epochs, we will stop the training and restore the weights from the best epoch. Alright, so let's run it. And while that's going, we can just start setting up the results. So first I'll evaluate the model on the test set. And then I want to create a classification report and a confusion matrix so we can see how it's doing within each class. So first let's get the true and predicted values. yTrue will just be a NumPy array of yTest, and yPred will be model.predictXTest. But we want to check if each value is over 0.5, so that will change it to true false. True if it's over 0.5, and then we can create an array around that with dtype numpy.int to give us integers with ones and zeros instead of trues and falses, which will be the same type as yTrue. But this actually comes as a two-dimensional array, so we're then going to squeeze it down to one dimension so that it takes the same form as yTrue. Then when we're done with that, we can print out the classification report. And call classification report excuse me, from sklearn. Let's pass in yTrue and yPred. And then we'll do a similar thing for the confusion matrix. Alright, and if we look at this, the validation loss, you can see it is right. It has not recovered from this value. This was its lowest, and it did not improve after 3 epochs, so it stopped the training, and it has restored the weights from the best epoch. So now let's evaluate. See how it does on the test set. Alright, so we got an accuracy of 91.6% and an AUC of 0.895. So very good, actually. You wouldn't think that these features would contain enough information, but let's actually see how it's doing within the underrepresented class. So we're going to create our predictions and our true values, and we're going to print the classification report and the confusion matrix. So this is actually still pretty good. This is very decent. You can see in the negative class, which was the much more populous class, we have extremely high scores, which is to be expected, since so many of the examples were negative. But then the other, what was it, 12%, 14.7% were positive, and you can see the scores are slightly lower, especially the recall, which means of all the actual, this is the percentage. Out of all of the actual positives, this is how many we predicted correctly. You can see out of the actual negatives, we predicted 98% of them correctly, but out of the positives, we only did 53%. So, you know, it's not so great in that respect. So here's our confusion matrix. This is true negatives, true positives. This is what we predicted negative, but was actually positive. And this is what we predicted positive, but was actually negative. So this is interesting. You can see is about 50-50. Like, just as the recall says, 53% of them, of the actual negatives, lie in the true value. So we did actually guess more of the negatives correctly than we, positives. We guessed more of the positives correctly than we did incorrectly. Alright, so that will sum up today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.